Okay, we're going to take a look at chapter 14 from volume 1 on fluid dynamics. So just a quick introduction before we start talking about what a fluid is. We need to look at the different states of matter because only a few of them can actually behave like a fluid. Actually, most of them can behave like a fluid, but the one that obviously is not a fluid is a solid. Of course, a liquid, a gas, and a plasma can all behave like a fluid because, as we'll see, all you need for a fluid is for something to flow. Basically, it has no elasticity in terms of shear. That's a little bit complicated, but it basically means that as it starts changing its shape, okay, it can't remember what its original shape was. Solids, you can actually have that. So usually the coldest state of matter is our solid. If we heat something up and it's under enough pressure, it becomes a liquid. At even higher temperatures, we tend to get gases. And at the very highest temperatures, the collisions between the gas molecules can be large enough where we start losing electrons and we transition to what's known as a plasma. So solids have a definite volume, okay? They also have a definite shape. And basically, this is because the molecules are held at specific locations. Now, most solids, or the atoms or molecules within a solid, can be modeled as masses on springs. So they are free to move from this equilibrium position, but the equilibrium position is really their average position. They can't stray too far from that. So, solid, again, definite volume, definite shape, and that definite shape is what makes the solid phase unique. In terms of solids, external forces can be applied to a solid to compress the material, okay? We'll often call these external forces distributed over an area stress. And when the force is removed, again, because the solid has a definite shape, it returns to its original shape and size if it's a true solid, and we haven't pushed it beyond what's called the elastic limit. Special types of solids include crystalline solids. These are solids that have, on a microscopic scale or a sub-microscopic scale, have a definite three-dimensional pattern to the way that the atoms or molecules are ordered. A very good example of this is sodium chloride. The gray spheres represent the sodium atoms or sodium ions in the salt crystal. The chlorine is represented by green here. And this is really one of the simplest crystals. It's a simple cubic. There are more complex types of crystals found in nature. And you can see a few of them here. It all depends on what the size of the individual atoms are, what the bonding angles are. All of these will affect the different crystalline shapes. Some solids don't have a definite three-dimensional pattern. We call these amorphous solids. Sometimes we call them glasses. And basically, a glass is a solid which has been cooled so quickly that the atoms haven't had time to arrange themselves into a definite three-dimensional pattern. Of course, we use the term glass for transparent media that we can look through. But yes, of course, plate glass is not crystalline. It's usually more durable because it's amorphous. It can't break or cleave along particular planes. Now, the difference between a liquid and a solid, liquids and solids have a very similar density to them, okay? And while a liquid has a definite volume, it has no definite shape. We put a liquid in a container, and it's going to take the shape of that particular container. Typically, we think of, for instance, like water. Liquid water exists at a higher temperature than ice. That's not always true, okay? Liquid doesn't happen unless there's external pressure, okay? Even though the molecules don't have any definite position, which they are at equilibrium, the molecules are free to wander about the liquid, but pretty much like the solid, they'll stay in contact with neighbor. Gas, no definite volume, and of course, no definite shape. Volumes are much lower density material than our liquid, and the molecules interact less frequently. Now, with the liquid molecules, they're constantly sliding past one another, so they're almost always in contact with a neighbor. With a gas, it's actually less frequent. Okay, most gases, the molecules rarely interact with one another. So what we have here is what's called a phase diagram. Here we can see pressure is in the vertical axis, temperature is in the horizontal axis. At low enough temperatures, high enough pressures, we get solids. As I said before, liquids don't exist at too low of a pressure. They do need some external pressure. Generally, they are at higher temperatures than solids. Gas is at a higher temperature than that. And then when we get enough heat into it, a material can begin to ionize and become a plasma. Now, it's important to understand that with plasmas, they can actually exist in different levels of plasma, meaning you can have, on average, 1 electron removed, 2 electrons removed, things like that. So a little bit more complicated than our neutral phases of matter, solid, liquid, and gas. Plasma usually exists at high temperatures. Lightning is a great example of a plasma. We see plasma in stellar nurseries where stars are newly forming, and we've got some very hot young stars that ionize the gas around them. We see plasmas in auroras, and auroras are where the solar wind interacts with the Earth's magnetic field, causing particles to crash into the upper atmosphere. Of course, we can use plasma actually for useful things, such as cutting into difficult materials, and also in plasma fusion. What's interesting, in the universe, what we consider normal matter, atoms, only makes up about 4% of the total matter in the universe. There's actually other forms of matter that are out there that we don't know very much about. In this chapter, of course, we're going to talk about normal matter, but there's dark matter, which you may have heard of. This may account for as much as 27% of the total matter in the universe. We're not sure what dark matter is made out of. It's probably made out of very weakly interacting particles, but probably isn't certainty. And the most mysterious of all of the matter, if it's even matter, is this stuff called dark energy. And we believe it is responsible for the acceleration of the universe. And as much as 70% of all the matter in the universe may be this dark energy. That's kind of a loose term for matter, because it really relies on this dark energy to have like a mass equivalence, E equals mc squared. But again, we really don't know what this dark energy is. Okay, let's get back to normal stuff. We're going to talk about the properties of fluids. Okay, fluids. So density of fluids and pressures of fluids. What are we talking about, and how are they related? Well, density is really quite simple. You've seen density before. Density is a substance's mass, okay? Of course, measured in kilograms if we're using SI units, or grams if we're using CGS, divided by the volume. So meters cubed for SI, centimeters cubed for CGS. Interestingly, we do talk about density, and we normalize it to water And this is what we call specific gravity. So if you ever hear the term specific gravity, it's really talking about density. And because water is 1 gram per cubic centimeter, the specific gravity is normalized to these units, even though it has no units. So density. So the density of most liquids and solids will vary with temperature, will vary with pressure. Liquids more so than solids. And densities of gases will vary a lot. In fact, later on in the semester, we're going to talk about the ideal gas equation, which says PV equals nRT. It relates the volume that a gas will occupy based on the pressure and the temperature. We can rewrite this. V is equal to nRT over P. So any change in pressure, any change in temperature is going to have a very large effect on the volume, and therefore a large effect on the density of a gas. Not so much for liquids and solids. They do change with pressure and temperature, but not by a tremendous amount. So here's some different densities of different substances, and we can see this in the SI units, okay? Because we have this in scientific notation, it's actually really easy to convert it into grams per cubic centimeter. Oops, that's not what I wanted to do. And if we just divide by 1,000, which is taking off that 10 to the 3, there's your specific gravity right there. Or there's your grams per cubic centimeter. See that down here too. Okay. Again, we can see for liquids and solids, the density can be anywhere from a little bit under 1, like ethyl alcohol and benzene. These are lower in density. All the way up to, I don't have osmium here, but platinum's pretty dense. Here we're talking about low 20s. Of course, when we look at the gases, their densities are much, much lower. Okay. And again, these are in kilograms per meter cubed. So you'd have to divide by 1,000 to get grams per centimeters cubed. And you can see air is about 1,000th of the density of water. And helium and hydrogen even less. And that's why they're buoyant when in regular air. And again, specific gravity, if we want a very precise definition for specific gravity, it is the density of a substance, the ratio of the density of a substance to the ratio to that density of water at 4 degrees centigrade, where liquid water is at its densest. Okay, what about pressure? Pressure is force. Oops, let me give a check. Pressure is force divided by area. So pressure is in units of newtons, okay? That's your unit of force, divided by your unit of area, which is meters squared, okay? And we call this a Pascal, okay? How many newtons are distributed over meters squared? Pascal is a very, very small unit of pressure. But again, it is the SI unit of pressure. And what we notice is that as we go deeper into a fluid, the weight of the fluid actually generates pressure, okay? All right, just jumping ahead a little bit, the pressure of the atmosphere is around 10 to the 5th pascals, right? So that atmospheric pressure is pushing down on the top of this fluid, okay? That actually comes from the weight of our own atmosphere. There's 10 to the 5 newtons of air pushing down on us for every square meter of the surface of the Earth. In addition to that, all the water overlying a particular body is going to add its own weight to this, and it's going to increase the amount of force. Weight is a force, and there's going to be more pressure. Okay? So at the top of an object submerged in a liquid, we actually have less pressure than all the way at the bottom, where there's even more fluid pushing down, generating more force. See, that's the interesting thing about the liquid pressure here. We think of gravity as pulling down, but the pressure, the internal pressure from a liquid will push on all sides. So this downward force is actually redirected against all the different surfaces. Okay. Now here's our equation for pressure as a function of depth. All right. Now this P naught term is the atmospheric pressure acting on a fluid. Okay. But the total pressure that a fluid will exert or experience is equal to the density of the fluid. Okay. We're talking about liquid water. We're usually talking about a density of 1,000 kilograms per meter cubed. So there's your density right there. Times the acceleration of gravity. So that's 9.8 meters per second squared, almost 10. And the height. Okay. So let's say that you're 1 meter down. You're submerged 1 meter in water. Well, you will experience about 10 to the 4 additional pascals of force from the weight of that water. If you dive 10 meters down, okay, roughly about 30 feet, you'll experience twice the atmospheric pressure, because that'll put you right around 10 to the 5th pascals on this term right here. And remember, normal atmospheric pressure, 10 to the 5th pascals. Okay. And again, regardless the shape of the container, this holds true for any depth. No matter where you are, at the same level as we cut through here, all the fluid at that level will have the same pressure. All the fluid down here will have the same pressure. All the fluid at the top will have the same pressure. Okay. It's just that the closer to the top you are, the less pressure you have. Okay, let's do some calculations here. Calculate the weight and pressure of a waterbed. Let's say the waterbed is 2 meters on each side. So 2 meters this way, 2 meters this way. I know it doesn't look like a square. Let's say it's a square. 2 meters by 2 meters, okay? And it's 30 centimeters deep, 0.30 meters deep, okay? Find its weight and find the pressure that the waterbed exerts. Okay, so the first thing you need to do is find out how much area this is. 2 times 2, that's really easy. There's 4 meters squared of surface area. Okay, but also we need to know this height right here is 0.30 meters. Okay, now if density is equal to mass divided by volume, and we want to find the weight, we want to find mg, what we need to do is m is rho times v, and we're going to multiply that by g, okay? So we're trying to find this one right here, all right? What is the density? Well, the density of water is easy. It's 10 to the 3 kilograms kilograms per meter cubed. What is a volume? 4 times 0.3, well, that's about 1.2 cubic meters times 9.8 meters per second squared. That'll give you the weight. Okay, so we're going to do that first. Okay, Here is the volume. As I said, it's 1.2 cubic meters. There is our expression for density. We can solve for mass. All right. So 1.2 times 10 to the 3 kilograms. Multiply that by 9.8. We get 1.18 times 10 to the 4 newtons. So we did the first part. We found out the weight. All right. Just remember, density is mass per volume. If you want the mass, it's density times volume. Okay, on to the next. Find the pressure that the water exerts on the bed. Okay, remember, pressure is force divided by area. We've already said the surface area of this is 4 square meters. So I take my weight, I take my area, and I get 2.95 times 10 to the 3 pascals. All right. Okay. That's pretty easy. Let's do something a little bit more difficult. An oil tanker's hull was breached. One of its tanks became flooded with salt water. The salt water has a density of 1.025 grams per cubic centimeter. On top of the water floats 8 meters of oil, with a density of 0.7 grams per cubic centimeter. Find the pressure due to the layers of fluid. Okay, now, problem here is we're given everything in grams per cubic centimeter. So we got to convert to CGS units. So I should say we've got to convert from CGS units. So we take our density of salt water. We know that there's 1 million cubic centimeters in 1 cubic meter. You can prove that to yourself, by the way, folks. A cubic meter is 100 centimeters by 100 centimeters by 100. 100 times 100 times 100 is 1 million. And then we want to convert grams into kilograms, so we divide by 1,000. So very simply, the density in kilograms meters cubed, all we need to do is just multiply by 1,000. And oil is 0.7, so we multiply that by 1,000, we get times 2. Okay, so we have the densities. Now, at the very top of the oil is atmospheric pressure, okay? 1.01 times 10 to the 5th pascals. Oftentimes, I'll just use 10 to the 5th pascals, okay? That is due to the weight of the atmosphere pushing down. The next layer has a pressure P1. That is from the weight of the oil, okay? Here's the density of the oil. Here's acceleration of gravity, okay? Here is the thickness here, okay? Just solving that part right here. So that gives us that P1 is equal to 1.56 times 10 to the 5 pascals. What about the pressure at the very bottom of this? What is that pressure? Well, you take the previous pressure, put it right here, add that to the density of the seawater times G times the depth, and we get the new pressure P2. Okay, so that's how much pressure is at the bottom of the tank, about 2 atmospheres. All right. Okay, that's it for this part.